Okay. And now it's on? Or? Yes. Hello. Yeah. Okay. Okay, good morning, everybody. I'd like to welcome you to our second day of Fringe, and I will co-convene this session with my colleague Björn Rom, and I'm Julia Kubanek. We both work at ESA Aztec in the Netherlands. And we are involved in the development and design of future missions, and we will have 4 presentations about our new missions. 2 presentations will be given by Björn, 1 will be given by myself, and 1 other presentation will be by Paul Pratz from DLR. We won't have questions after the presentations, but we will have a roundtable discussion in the end of the session. So the first presentation will be given by Björn Rom, and it will be about our Earth Explorer mission, Biomass.
Thank you, Julia. Good morning, everyone. Is this one working? Now it works. Closer, like this. Okay, let's see. Or I speak a little bit louder. Okay, good morning, everyone. So welcome to this presentation this morning, and welcome to be here so early in the morning with this fantastic weather here outside. The overview, I will talk about, let's say, the overview and preparation status of ESA's Earth Explorer 7 biomass mission. It was good to see yesterday as well quite some young people here, and I hope not everyone has already seen a biomass presentation, so you may be amazed. And people have already seen it, sorry for some slides that you will have seen before. But of course, I've tried to put in some new material as well. So his presentation is co-authored by my colleagues Philip Willemsen, Tristan Simon, Antonio Leanza, Sergio Bras, and Michael Verringer, the project manager of Biomass, all based at ESA Aztec in the Netherlands. So a bit of an overview of the mission objectives. Then I will start a bit with the key mission requirements of the Biomass mission, mission operations concept, the system architecture, and the current status and outlook. Here you see a very nice, let's say, picture of how the satellite actually looks like. With a 12.5 meter reflector antenna with a feed array on the satellite itself. So the overall mission summary of Biomass. So the overall main, let's say, activity of the mission is to take stock of biomass in the world's forest and to monitor its evolution. Just as a side note, let's say it's not good to name a mission the same way as its main mission product. Because it confuses everyone, but okay, this was already done in the past. But So the mission is named biomass, and it will also look for biomass. So the primary objectives are determination of forest biomass, and it's given its name, forest height, and vegetation disturbances and regrowth. Then, of course, they will also have secondary objectives, because we're flying for the first time a P-band SAR sensor in space. We'll be able to image subsurface geology in deserts, looking at water paleo rivers, mapping topography under dense vegetation. So it will be the first time, because of the penetration capability of P-band, it will also be able to see the topography underneath the forest, providing for the first time our eyes to look at, say, a digital terrain model under the forest itself. And measurements of glacier and ice sheet velocities. And of course, there are much more, like was also mentioned yesterday, for example, let's say ionospheric mapping. So what information we will get from biomass? Of course, let's say the forest biomass itself, looking at above ground biomass, which is typically, let's say, provided in tons per hectare, which is a product that's given a 200-meter resolution. So it's a 6-look product. One map roughly every 9 months during the informatic phase. I will come back, let's say, to the phase of the mission later. And we have a global coverage of forest areas outside of areas where we're not allowed to transmit, which is given by the Space Object Tracking Radar Network, which is operated mostly, say, in the US and over Europe. The overall accuracy will be 20% or 10 tons per hectare for biomass values less than 50 tons per hectare. Then as well, let's say, upper canopy height. So again, it's 200-meter resolution. Again, we have to provide one map every 9 months. Global coverage of forest areas and accuracy of around 20 to 30%. And then disturbances, which is actually given, let's say, a high resolution product, so 50-meter resolution. One map roughly every 6 months for 4 years. It should actually be also 9 months, so apologies for the error there. Global coverage of forested areas, again, saying the 90% specification accuracy. So overall, let's say the resolution, let's say we'll have let's say 55 meter. So the SAR observation capability we'll be able to do with biomass because of fully polarimetric features. We'll be able to do SAR polarimetry. That's basically what you see on the left. Able to get, let's say, the intensity values in a gridded pixels. Then because of the SAR informatic capability, by having suitable baselines, we'll be able as well to get access to the height. And then what is something that is a feature of biomass itself, this will be the first mission which will have an actual tomographic phase, dedicated tomographic phase. We'll be able to do SAR tomography by making sure we have up to 7, let's say, repeats over a given area within a given amount of time, where we'll be able to get, let's say, access to the overall forest intensity as a function of the height. So we'll be able to penetrate within the forest. Key mission requirements, so it's a fully polarimetric P-band SAR. As mentioned before, there's a sensitivity to biomass compared to other wavelengths. It has a very good penetration, displays a high temporal coherence of repeat passes. But of course, it also has some downsides. P-band for space applications poses quite some challenges. P-band is very susceptible to ionospheric distortions. And because of the large wavelength, of course, everything scales with it. With a large antenna diameter, and the combination of both the antenna and the feed is so large. And as well, because of the large wavelength, there are no facilities where we will be able to characterize everything in an end-to-end performance testing on the ground. So which means we have to rely on a dedicated, we have to rely on let's say, modeled patterns and do a dedicated antenna pattern characterization in orbit. To achieve the required level 2 performance, system is to comply with high accuracy polarimetric radiometric requirements, and SAR working in quad-pol, which means that we get all the scattering coefficients, different linear combinations. We have 2 mission phases employing multi-pass interferometry, so we have a controlled inter-orbit distances to baselines between successive orbits, successive revisits to the same site. So we have a dedicated tomographic phase where the mission will start with up to 6 3-day baselines, so 7 acquisitions in total, and for the informatic phase, which will be continued after and will be repeated until the end of the mission lifetime, will be observations with 2 3-day baselines, so 3 acquisitions. So key mission characteristics: a sun-synchronous orbit at 666 kilometers, down dusk, 6 a.m. ascending, 3-day repeat with the 44 orbits in total. We have a small east-west drift to implement the baseline, so we'll come to that, let's say, very detailed, so you really understand how actually we're going to operate the mission. We have 6 megahertz bandwidth at P-band, so 432 to 438 megahertz. And we have a satellite role for SWAT access. So this is a strip map, SAR, no fancy digital beamforming, I'm sorry, this is what it is. And we have to to get access to the next swath, we have a mechanical roll, which means we can't do it at the same time. We have to come up the next time and then roll the satellite to get access to the next swath. Okay, thank you. And the satellite repositioning maneuver after each major cycle, and I come to that later as well. So what you see here is basically a 3-day, on the right you see a 3-day coverage from a given swath. Roughly, let's say, as you see, let's say around 50 kilometers each swath. So total, let's say, for the 2 swaths, this is swath 2, this is swath 3, and the combination is about this, let's say, if you would be able to capture everything together in what we call a single major cycle. The overall, let's say, swath, the combined swath is about 150 kilometers this way. So the observation geometry, so the 1-day coverage, this is what you have, let's say, with in 1 day. This is actually the 3-day coverage, so the 44 orbits that I mentioned. Of course, when you have a spacecraft in orbit with a pure 3 days, 44 orbits, it will observe exactly the same area every 3 days. So we will never be able to get global coverage this way, typically. What we do is to have a small, let's say, longitude drift. So what we actually operate biomass at slightly higher altitude than this 44 orbits, let's say, fixed repeat, which means that the spacecraft will take a little bit longer than 3 days to perform the 44 orbits, and the Earth will have enough time to slightly rotate a little bit more eastwards, which actually gives us this longitude drift, which gives us the necessary baselines. So for the observation geometry for SWAT 1, the biomass will stay always in this, for tomographic coverage, as indicated, we will have about 7 acquisitions. For the interferometric coverage, we have 3 acquisitions. Of course, if it would stay in this drifting orbit, then of course it will take too long to achieve global coverage that way. A solution there is to roll the roll maneuver, as I mentioned, and then we just repeat. So what you see every time, every acquisition is basically a 3-day temporal baseline between the previous one. And the same for SWAT 3. So here you see the combination of the 3 SWATs and showing that actually we do a mechanical roll. Then there's a limit, let's say, to the possible instance angle for the observation itself. Also, this is mainly driven by the retrieval, and as well as by the radar timeline. So at the end of the observations with the 3 SWATs, biomass raises its orbit, so we increase the longitude drift rate. And by this, actually, we can jump to the next, let's say, start of the next position after the SWAT 3, where we then continue SWAT 1 again. That's what you see basically here. So putting this all together, this is basically what you see here after SWAT 1, 2, and 3, where we have multiple acquisitions for each of the SWATs with a 3-day baseline, temporal baseline, and this is what we call a major cycle. You see, after one major cycle, we have huge gaps. So then, indeed, what we have to do then, we have to do the satellite repositioning maneuver. We raise the orbit, have a faster longitude drift, and then lower the spacecraft again. Repeat this procedure, and after 7 of these major cycles, we will be able to complete the overall global coverage. As you can see, this takes much longer than any other, let's say, like Sentinel-1. We're going to do all this in 12 days. For biomass, because of all the temporal baselines, this will take roughly 9 months in the interferometric phase, and in the tomographic phase, it takes 17 months, and it's at the beginning of mission lifetime, where we do the tomography. So, and then of course, then it's back, let's say, at these dots, at these arrows, and then we start again, say, the next global cycle. Okay, now what I've just been telling you, we've got a very nice animation, so I will show you this one, then it will also be very clear to you how actually, and hopefully this will stick better than just my words. So this is how it will operate, let's say, for a given swath. Then after what we call a minor cycle, after completing, let's say, the revisit of the swaths, of the given swath, we have to do this roll maneuver, which is something that we do over the pole. That's what you see here. We continue in the second swath. So I think you get the idea now. And of course, after the second swath, we complete, let's say, we do again this roll maneuver and start, let's say, the third swath. So after completing then this third swath, as I told you, let's say, then we have to jump basically over these ribbons and start, let's say, on the west part, let's say, of it, a new acquisition profile. Of course, what I've shown here is only for the ascending, but of course the same goes for the descending. Here you see so you see this maneuver is quite intrinsic, because there's a bit of rock and roll involved here. So you see the thrusters going and actually goes to a slightly higher orbit, a couple of kilometers, where the drift will be higher. Then during this, what is not shown here, okay, now it rolls back. During this drift, we'll still be able to do acquisitions. Of course, they will not be interferometric, because they'll only be during the longitude drift, but for all intensity-based, polarimetry-based, we'll be able to do it. And after this, let's say, roughly, between 9 and 12 days, we'll lower the satellite again, and then we'll continue the observation again, what you see here. Then another interesting thing to show is because it's a left-looking SAR, and people are so used to right-looking SAR that they forget that this is actually for the Antarctic. You will have a very nice coverage with biomass, and this actually shows, let's say, the overall global coverage of the mission. But then, especially when you focus, let's say, on the Antarctic, you'll see that the hole there, let's say, is definitely smaller than what we see with other missions. And this overall build-up, as I said, let's say, is roughly, let's say, 9 months. It will take 9 months for the interferometric phase. And of course, one of the secondary objectives is actually looking at, let's say, ice sheet velocities. The ground segment overview. The ground segment is composed, let's say, of a couple of elements, quite standard elements. We have a flight operations segment, monitoring and operating the biomass mission. So it's overall mission, telemetry, telecommand, so communication with the spacecraft, mission planning, satellite control, status monitoring, orbit attitude determination, onboard software maintenance. Then we have the PDGS, implementing all science data functions, so payload, X-band, acquisition planning, science data, payload data processing, and provision of data access. Then we have something where I want to, let's say, which is, okay, I think quite standard, let's say, for SAR missions. We have, of course, we need to calibrate the system. For this, I say we have a calibration transponder as our main instrument for the overall calibration. Of course, it's not the only thing we're doing. We're looking as well at distributed targets. We're looking at targets of opportunity. But this is the only thing where we'll be able to do the full end-to-end with. Of course, the fact that it's a P-band, things grow as well. So this will be, and I will show a couple of slides on the transponder itself. It's going to be located in Western Australia, ESA's New Norcia site. The antenna diameter that you see there on this phased array, the circular phased array, is about 4.9 meters, so just below 5 meters. So, and I can tell you this is quite big if you stand in front of it. So it's first of its kind, this polarimetric active radar calibrator. 4 independent polarimetric signature matrices. You'll be able to track the satellite in azimuth elevation, so it's a bit, let's say, as you see there, it's a bit pan-tilt unit, which is as well quite large. As you see here, this is the overall transponder, how it looks like. Let's say you see at the bottom, you see basically a door, an access door. So then get a little bit of an idea of the actual size of this infrastructure. So we have as well a calibration subsystem, which will be placed together with the transponder to do this, support the transponder external calibration during its lifetime as well. So the deployment of this radar calibrator, the transponder is ongoing. Say this was in spring this year, where the radome has been put, let's say, over the 4.9 meter. You will see on the left top, you will think it probably will not fit, but it did fit. So the radome was successfully put over the array. And then the road to the phase E2. So where are we now, and what is the actual schedule? What we're going to do? So now We started, let's say, with the in-orbit commissioning, ramping up activities end of last year. By the end of this year, we'll have an integrated team preparation of activities. By the end of this year, Q4 23. Then we'll start, let's say, the in-orbit commissioning activities rehearsal, T0 minus 4 months, where T0 is the biomass launch. Then we have an in-orbit commissioning, roughly, let's say, 6 months. And after 6 months, biomass enters in phase E2. So the overall mission timeline, we have a nominal mission duration of 5.5 years. Commissioning phase of smaller than 6 months. As I mentioned, tomographic phase of smaller than 17 months. And then a number of interferometric coverages, which take each less than 9 months. And this will be until the end of mission lifetime. Now, as you've seen, the way we have to operate it, by controlling the baselines, by let's say this kind of grasshopping approach where we have to jump over the swaths. This, of course, will cost, let's say, some delta V. So the fuel, let's say the mission will be limited, let's say, by the fuel consumption that is likely to run out. Okay, not maybe directly after 5.5 years, but probably, let's say, closely after, let's say, 6 years. So this will not be a mission that will be there for 10 years, unfortunately. And this is because of the very specific operational profile of the biomass mission. So now back to actually the actual hardware. So of course you've seen very nice animations of the biomass mission, but of course the mission is actually being realized right now, and we're close to the end of the phase D, which is the actual development phase, and we're now working on, let's say, the actual assembly, integration, and tests. So what you see here on the right is the fully assembled satellite together with the large deployable reflector, which is in the stowed configuration. We cannot say there's only one facility where we can actually deploy the deployment test, and it's in Florida in the US at L3H. And here you see as well some pictures of the overall satellite, let's say. Let's say, they see as well the solar array deployment. We, of course, have to be hanging on cables to just mimic a bit of microgravity, otherwise they would break. Yeah, it's fine, I'm nearly finished, thank you. And on the right, you see the actual the payload panel, the satellite open with the payload panel mounted, so with all the major hardware already integrated. So this is my last slide. So there are some open issues. Biomass has recently been moved from Vega to Vega C. Some of you probably have heard that in December last year, there was a problem with the Vega C launch, carrying 2 Pleiades satellites to orbit. They lost trust, and now there was an investigation board. Before summer as well, there was another investigation board started because of some other issues they found. They're currently working on this. Biomass was on the Vega launcher initially, but it will now be moved to Vega C in order, let's say, for Arianespace to move the remaining 3 Vega launches to do them within the next year. And biomass will only be ready for launch towards the end of next year. It means that we're going to be moved to Vega C. There's a late delivery of the power amplifier system, subsystem. So these 2 issues are the main open issues right now. Satellite passed part of the final environmental test campaign, and all other remaining work is of the critical path. So what are the key upcoming milestones for biomass? The PAS will be the power amplifier subsystem product flight model will be available in December. And this is really the missing element for the instrument completion and final tests to be done. Duration from the point of delivery of the full instrument until, let's say, launch readiness is 10 to 12 months. Launch readiness means basically the next day you will be able to launch. The continuation of the environmental test campaign, so thermal vacuum, electromagnetic compatibility, etc., will start, let's say, in Q2 24. And then the qualification acceptance review is basically the flight acceptance will be in August, September next year, within a launch readiness in Q4 24. So with a bit of luck and a bit of confirmation from the availability of the Vega C launch and the return to flight of Vega C, as I think it was mentioned yesterday, Sentinel-1C will be the first passenger, and hopefully biomass will be maybe the second or maybe the third passenger. But this will be confirmed in hopefully in a few weeks' time, and then we should have biomass there, hopefully in 25, and hopefully later in 25 we should be able to deliver products to users. So this concludes my presentation. Thank you. One last point, there's an announcement of BioGeoSAR 23 will be given, let's say, and there will be a small workshop in Rome, 15th to 17th of November this year is retrieval of biogeophysical parameters from SAR data for land applications. It's always organized around following themes: land use, agriculture, soil and hydrology, forestry, ice and snow. It's a very nice, small community workshop. You're welcome to join. Abstract submission is closing 18th of September, so hurry up. Thank you. Okay, without further ado, we move then to the next presenter. That's my colleague Julia Kubinek, also from ESA Aztec. And she will present the future Copernicus SAR mission constellation Roselle and Sentinel-1 next generation. Okay, Julia, the floor is yours.
Thank you, Björn. Good morning again, everybody. I'm pleased to give this presentation on behalf of a very big team behind. A few authors are listed here. Responsible for the mission science behind both of the missions are Malcolm Davidson, myself, and Lorenzo Giannini. And then we have the project managers Ramon Torres and Gianluigi Di Cosimo. So I would like to start with the general Copernicus SAR context. Most of you know the current generation of Sentinels, which not only includes Sentinel-1 A and B and C and D, but many other missions. But I've just highlighted here the C-band radar as a SAR, in the SAR context. We are also developing the next generation of Sentinels, of which part is Sentinel-1 next generation in C-band, which I will be focusing on in this presentation. And then we also have the Copernicus expansion missions. And within this framework, we are developing the Roselle mission, which will be an L-band radar system for monitoring in the Arctic, the cryosphere, land and emergency mapping, and ground motion and soil moisture. We have seen this Copernicus timeline yesterday already of the current and future SAR missions. So we talked about Sentinel-1A and B and the upcoming launch of Sentinel-1C, and also that D is already there to be launched in the future. And in this presentation, I focus on Roselle and Sentinel-1 next generation, which both will enhance the continuity of the current system, so our current Sentinel-1 system, but also to address gaps particularly by the new radar wavelength we are adding to here. So I will start talking about Sentinel-1 next generation. It's a mission in development, and here I've put some driving requirements and objectives. So it's really driven by the enhanced the continuity of the services that we are already serving with Sentinel-1 and the applications that rely on the satellite mission. But we would also like to enhance the existing services and applications and also enable new applications, for instance, by building on the improved performance and observation gaps. So also a better resolution, a better revisit will lead to new products and applications in the end. Some mission and system requirements. So we base many of the requirements on the Sentinel-1 mission, and we define here that the performance shall be equal or better than Sentinel-1. FG means here first generation, which is used a lot in the radar context now for the Sentinel-1 mission. The revisit should be 3 days global, 0.5 days in the Arctic and for sea ice. The resolution should be better than 25 square meters or equal to. We are considering a very low noise, so minus 26 dB. Full continuity in dual pole and quad pole. The use of a dedicated mode to cover the North Pole region. And also the same orbit as Sentinel-1 first generation and also Roselle. So the missions are developed really in a context together and not as separate missions. Here is a look on the Copernicus services. So we studied the user needs from the European Commission, from the Polar Expert Group, and many different other user groups to see and to decide what the mission should focus on. I mentioned this enhanced and to ensure the continuity, and you see like the different services here focusing on sea ice, type, concentration, motion, on ground movements, ocean currents, vessel detection, oil spill, location and morphology, soil moisture in general, land use mapping. So with the Sentinel-1 Next Generation mission, we will really serve like all these, or ensure that these services will continue and be better in the future. Here an overview of the requirements for Sentinel-1 that we defined compared to Sentinel-1. I mentioned already this North Pole mode, so the latitude coverage should be from -80 to +90 degrees, which was not available for Sentinel-1. The revisit is 3 days global, half a day in the Arctic and for sea ice, which was also like very different for Sentinel-1. Latency, 10 minutes over European waters and 120 minutes global. Repeat pass stays the same, 6 days for constellation of 2 satellites and 12 days for 1 satellite, which will also be the same for ROSE-L. Incidence angle axis is for Sentinel-1 20 to 45 degrees, and this should be met by Sentinel-1 Next Generation and should be better than this. We are focusing on a very large swath covering 400 kilometers, resolution 25 square meters, I mentioned this, and also the low noise. With respect to polarization, we will also include quad pole and also the duty cycle. Nuno mentioned it yesterday for Sentinel-1 with the 25 to 30 minutes. We will have roughly 43 minutes per orbit. Other requirements include the potential of the integration of additional satellites into the mission, so really focusing as an anchor satellite mission of systems. AIS will also be as a payload on board, which is already included for Sentinel-1 C and D, so we will augment the service here. And also a wave mode shall be available over the ocean. Here, an overview of the high resolution. So on the left, you see an image from a campaign that was flown, like an airborne campaign, many years ago with DLR system. And so generating high resolution images because it's airborne. And in the center, potential Sentinel-1 NG 5-meter resolution, and then compared to this, the Sentinel-1 interferometric white swath image. The lower noise equivalent sigma 0 will further enhance different applications, for instance, sea ice, but also soil moisture and oil spills and general mapping purposes. Some programmatic aspects. The phase 0 was carried out between 19 and 20. Then phase AB1 was kicked off and took 2 years from 21 to 23 with 2 different consortia in parallel. So we always start with 2 consortia and in the end select 1 to develop the satellite mission. And the ITT for the next development phases, so B2CDE1, will be issued very likely in November 23. So the team is working on this to define the parameters now. The expected launch is sometime after 2032. Here, yes, a very short overview of the phase A candidate concepts. So we had Airbus Defence and Space and Thales Italy. We had some constraints because the launcher should be a Vega C, and they should meet like a technology readiness at the end of phase A. That's always defined what should be reached by the end of which phase. So both concepts dealt with planar array antennas and reflector antennas, and in the end planar array antennas were selected by both consortia. And the instrument is based on SCORE, so digital beamforming and elevation, and the MAPS concept on ground in Azimut. And both ScanSAR and StripMet modes are proposed, and also the AIS instrument was part of the contracts to provide continuity, which will be established soon with Sentinel-1C and D. That's just a quick look about, or like introduction into this scan and receive and elevation, which is called SCORE, and multiple apertures and azimut maps. I think I'm not the right person to talk about this. I think it would, if there are questions, we can discuss this later. But it can also already be found in literature. Then I jump over to the WOS-L mission. WOS-L in general will be an L-band SAR with dual pole and quad pole modes. We will have a wave mode capability here too, resolution smaller than 50 square meters. And here you see like this IRWS mode, which is simply the WOS-L interferometric wide swath mode. Noise equivalent sigma 0 better than minus 28 dB, swath width larger than 250 kilometers. Also for WOS-L, we will fly 2 satellites, and different options for co-flyers are also under study. The consortium, so here the industry contract is already allocated. The consortium is led by Thales Alenia Space, involving 29 companies from 15 countries. And also here we really focus on the service continuity of Sentinel-1 and Sentinel-1 Next Generation. The coverage should be global land and excluding Antarctica, but including also here the Arctic. The revisit with 2 satellites is 6 days, global land, 3 days for Europe, and 1 day in the Arctic. And the repeat cycle of 6 days over global land is met by the 2 satellites, so it's very similar to Sentinel-1. Regarding programmatics, we are currently at the beginning of phase C. We will support the development of the mission with different science study activities, which will be led by myself and my colleagues. And we will issue an ITT for an ionospheric study of L-band products by the end of the year. The expected launch of PFM, which means pre-flight model, is expected in 2028, so the first satellite, and the flight model 2, so FM2, will be delivered in 2030. That's at least our expectation. Regarding some system aspects, so we focus really on a synergetic acquisition with Sentinel-1, so the swaths are co-located to support also convoy configuration. Latency is 10 minutes Europe coastal waters and 200 minutes for global. And we have the mission will also be companion friendly for single pass interferometry in case if there would be a co-flyer supporting the mission. Also here, I'd like to jump quickly into the different services. It is quite similar to what I showed to Sentinel-1 because WOS-L will focus on the gaps that are currently not served by our Sentinel fleet. And this image is a bit different, but we have the services also included, but more mentioned here, listed the applications and which services they would contribute to. So it's definitely geohazards monitoring, land use, agriculture and forestry, soil moisture products, cryospheric research and the Arctic, so also sea ice concentrations, icebergs, grounding lines, marine monitoring like swell properties and ocean surface winds, and maritime monitoring including icebergs, oil spills, location and morphology. Some examples here, so maybe to mention that we are in a collaboration with JAXA acquiring L-band data over selected target sites to really study synergies and complementarities of L and C-band data. And there will be a dedicated session on this with a few presentations on Friday morning. So here you see L-band compared to C-band, and you can see here these black circles where you get some deformation patterns which are not visible in the C-band. Both data also cover additionally different time scales, and it's also an area where we would have a lot of snow and vegetation, so L-band definitely helps here to bridge a gap in what Sentinel-1 could see and not see. In the figure below, that's maybe to mention, so we are supporting the development of the missions a lot with ground-based and airborne campaigns. I mentioned this before. And here we had a tower with radar antennas installed in a boreal forest in Sweden together with Chalmers University, looking at this boreal forest in P-band, C-band, and L-band, so it also supported the biomass mission, and you could nicely see the breathing of the trees in the data. There are a few publications out from the team, and the data sets are freely available on our campaign server. One other example is biomass and land use and land cover mapping, where L-band will definitely help to map and estimate the biomass, also to monitor deforestation, for instance by logging, and the losses of vegetation in general, and also land use and land cover mapping will definitely have an advantage of using the two different wavelengths at the same time. You can also see here some images of Sentinel-1 and ALOS-2 compared to get an overview of the different information you would be able to retrieve in the context of biomass and land use and land cover mapping. Regarding soil moisture, I think C and L band are also very complementary, where when the C band looks like in the first centimeter, L band can penetrate a bit deeper and maybe give up to 5 centimeters soil moisture in depth. You see here on the left, it's a field which was monitored during an airborne campaign with data acquired in L and C band. And you can see, the backscattering here. And the other figures also present a study of different crops and different polarizations from Sentinel-1 and ALOS-2 in a comparison to see what L-band and C-band can bring. That's both from Jülich in Germany. Then some words about sea ice monitoring. Also here you can see a RadarSat image compared to an ALOS image on the right, and you can nicely see similar patterns but also different ones. We had a study running to investigate C and L-band synergies, and for instance, young first-year ice is much better visible in L-band, and also icebergs are much better visible. This is also shown on the next slide. This was more focusing on vessel monitoring. So there's every year or every other year an experiment in the Baltic or North Sea where popcorn is spilled in the ocean to mimic oil spills. And we had ALOS data acquired at the time of this fake oil spill, and you could see the signatures very nicely in the data. So some information on SAR imaging and systematic acquisitions of ROSE-L. So as current baseline, the instrument provides 2 ScanSAR wide swath modes and a wave mode over the open ocean. You can see here in this table the different modes, so the ROSE-L interferometric wide swath mode, the quad-pole interferometric wide swath, and the wave mode. We have also here some sizing requirements, so the system should be always turned on over Europe, so similar to Sentinel-1, also for the Arctic and coastal Antarctica, and over global tectonic areas in dual or quad pulsar mode, and full coverage of the remaining land masses, which are not included in this, should have like a 12-day revisit time or 6-day depending on the number of satellites that are up. And dual or quad-pole mode needs to be decided on the application. And then the rest in wave mode over open ocean. For continuous operation, we have about 35 minutes in dual pulsar mode or 20 minutes in quad pulsar mode, and then the rest of the time it would be turned on in wave mode over the ocean when the orbit allows. Some design highlights of the constellation. I've mentioned a few of them already, but I wanted to put an emphasis here. that we really plan to have a synergistic acquisition plan and mission design with Sentinel-1 and then Sentinel-1 Next Generation. We fly in the same orbit as Sentinel-1. Sentinel-1 Next Generation will have the same orbit, and the phasing of the orbital plane is adjusted to follow the same ground track of Sentinel, and the OSL interferometric right swath mode guarantees a full swath overlap with Sentinel-1 interferometric right swath mode. The mission design supports at the moment a convoy concept where the satellites fly very shortly after each other or with a larger distance. It depends a bit on which application you ask, what the community wants, and we need to find a trade-off here. It's not decided yet. With the mission, we plan to generate a new archive of L-band data with consistent, good coherence. We have a duty cycle of 38 minutes in orbit in general, and the data will be, like for Sentinel-1, free and fully open to the community. And we are really moving forward here into a system of system concept with enhanced information products, and expect many new services to come out from C and L-band. That's on the science moment, but I think I'm running a bit over time, so I think I skip it. But also just to mention that the score and maps are also employed for ROSL, similar to what I mentioned for Sentinel-1 NG. So then I come to my conclusions. So it's just a very summary of what I said. So Sentinel-1 Next Generation is really meant to ensure the continuity and expansion of the services that we are currently serving with Sentinel-1 and all the applications and services that are relying on our satellite mission. Then to enhance these existing services and applications, and also to enable new applications by building on the improved performance on a better revisit and a better resolution. We will bring new enhanced capabilities with a higher resolution, with a lower noise and the wider swath, which I think is really nice because it improves the revisit a lot. ROSL at the same time will also bring new enhanced capabilities to address information gaps so that we can establish services and answer questions that we cannot currently answer with Sentinel-1 and will not be able to answer with Sentinel-1 Next Generation. We have a high resolution, a low noise, and a high duty cycle, and we also call it internally the mapping machine. So all these missions are addressed in a system and not in isolation, and that's very nice for us also to see what the missions will do all together in the future. That's all. Thank you for your attention. Okay, with this, we move to the next presenter, which will be my colleague Björn Romm, again, who's a mission scientist of the latest selected Earth Explorer mission, Harmony.
Good morning again. Yes, so I think to add a bit on what Julia just mentioned, of course you notice that Sentinel-1 and ROSL will fly in the same orbit. Now I've got some additional surprise for you. Also Harmony will be there. So you will have, let's say, by roughly, let's say, 2030, you will have a real train of radar satellites all moving within, let's say, 5 minutes from each other. So Harmony is now tagged as the ESA's Dynamic Services Mission, and I will come back later, let's say, why we call it this way. As you can see already from this graph, is that of course we're looking at 3 different, let's say, aspects, let's say, in the overall Earth system: solid Earth, land ice, and the ocean, as the primary objectives for this mission. So to come, let's say, to talk about how Harmony fits in an ESA's Earth observation mission landscape. You've heard about Copernicus. I've mentioned already, let's say, a bit about biomass earlier this morning. In ESA, we have an ESA Earth observation. We have basically 3 main pillars. One is basically the science, Earth observation science, which started with ERS-1, ERS-2, and VSAT, and then later we started the Earth Explorers, but also we have as well the Scout missions, and we have as well some other additional missions there, Earthwatch missions like THRUDS. So you see here, basically then, okay, biomass, you see biomass there, I think, when it's supposed to be launched shortly after 2020 to 2023, which I told you to say, which probably will be roughly the same now, 25. But you see as well there, Harmony just before 2030, ready to be launched around that time frame. Then of course the Copernicus missions, where you know about Sentinel-1, Sentinel-1 Next Generation, Roselle, which is part of the Copernicus framework, which is not basically, these are not the Earth science flagships that the Earth Explorers are, but more operational Earth observation missions. And then we have a meteorological pillar, which we do mostly, let's say, in cooperation with EUMETSAT, which is looking at the meteorological, let's say, satellites from both geostationary and low Earth orbit. So what happened last year, in September last year, basically ESA selected Harmony as the 10th Earth Explorer mission, which meant we had concluded, let's say, the original feasibility assessments, and now the mission, the project is fully implemented and on its way for meeting, let's say, the launch just before 2030. So Harmony in a nutshell, Harmony is ESA's Earth Explorer 10 mission, comprised of 2 companion satellites. We'll fly in, let's say, loose convoy with Sentinel-1D, long track separation around 350 kilometers, and its payload suite consists of a passive SAR and a multi-view thermal infrared instrument. So you can see that we have different configurations. What you see on the left is basically where we have a cross-track interferometric phase, where we're covering land applications, glaciers, permafrost volcanoes. Obviously, when we are launching, we'll be launching the 2 satellites together, which means that they're already close once we launch them, so we keep them for this during the, of course, during commissioning phase, and afterwards we have the first year where we keep the 2 systems in a cross-track interferometric configuration. Then during the years afterwards, so we move into this stereo phase, covering 3D surface deformation, mostly looking at accessing, let's say, for solid Earth, being able to access as well, let's say, the famous north-south displacements that the community has been asking for a long period of time. But as well, of the ocean, we'll be able to look at surface motion, surface winds, sea surface temperature, and cloud motion. And one thing you can see, you can actually compare it a bit, let's say, the configuration that we have is not exactly the same, but like, let's say, spectrometry, where you will be able to, because of the multiple line of sight, you'll be able to get more information about the actual things happening at the surface, both in intensity, but also, let's say, in velocities. So Harmony is really, let's say, what we call, let's say, tri-mode Earth system mission. So as I mentioned, say, we look really at the upper oceans, ocean-atmosphere interactions. This is also where the thermal infrared comes into play, where we're able, let's say, to look at cloud motion. We're able to see surface temperature and combine this with what actually the radar will see, and look at sea surface motion. We're able to address ocean mesoscale, sub-mesoscale features, upper ocean, and air-sea interaction processes. Then land ice and sea ice, and tectonic strain and volcanic processes. Of course, during this presentation, I will mostly focus on the land applications of Harmony. So, bringing Harmony to a dynamic world, Harmony will resolve really sub-kilometer scale motion vectors and topography changes associated to dynamic Earth system processes. So, over the ocean, we look at heat gas, momentum exchange at the air-sea interface, the upper ocean, mesoscale, sub-mesoscale, but as well look at the inner structure of ocean atmosphere extremes, so both tropical and extratropical cyclones, and try to get, let's say, to understand better, let's say, what's happening in the inner structure of these large systems. And gradual dynamic volume changes of global mountain and polar glaciers. As a secondary objective, we also look at instantaneous sea ice motion to characterize sea ice dynamics. And for the solid Earth, 3D deformation vectors associated to tectonic strain and topographic change at active volcanoes worldwide, which is also a secondary objective of the mission. So Harmony is a mission that's observing, let's say, looking at the small scale. So why do you want to look at these small scales? The Earth system, as you know, is highly nonlinear, which means that cascades of energy is flowing, let's say, from the large scale and to small scale and vice versa. So it's complex couplings and feedbacks between these processes at the different scales. The small processes, let's say, order less than 1 kilometer, and the couplings in the Earth system models are currently, let's say, not well described or understood, and they represent major uncertainties in the final outcome of these Earth system models. So harmony is a really mission that's looking most, let's say, to provide observations that are needed to develop, and train, and validate the next generation of fully coupled Earth system models. There was a final report, it was made as a report of mission selection at the end of, let's say, mid last year, which is available basically at this, which will give you much more information about the actual, all the science and the actual science objective of the mission itself. So for the cryosphere, Harmony will look, let's say, at 3D ice dynamics, as well climate glacier changes, and rapid dynamic glacier changes. And as secondary objectives, we'll look at, say, sea ice deformation, and also permafrost erosion and subsidence. So looking at topographic changes, and you'll see the little animation on top that is for during the cross-track interferometric phase. What is typically, let's say, needed is both getting observations for both, let's say, slow and gradual glacier changes, but as well on the rapid glacier changes. So, and this has been, let's say, of course, we have information, most, let's say, about half of the global glaciers worldwide, but with different, let's say, sensors, different methods, which leads to quite an inconsistent, let's say, interpretation of all these results. What you see on the left is typically, let's say, in the order, let's say, of meters per year glacier changes, which was done between SRTM and TandemX between 2000 and 2012. Then, of course, in intermediate, you will have basically looking at something in the order, let's say, 50 meters over a couple of months, where you see that with low spatial resolution, you may not always get, let's say, access to the full picture. With TandemX, of course, this was provided then. And then for sudden collapses, what you see there, which is in the order of hundreds of meters in minutes. So what you see there in this collapse, this glacier collapse in Tibet in 2016. So what we need there is we need simultaneous high repeat topographic and lateral ice motion. So then in this other phase, let's say when we are flying, let's say, in stereo, then of course Harmony will be able to get this 3D deformation. So what is currently done, of course, with current observations, we mostly get, let's say, 2 components, and the third component, let's say, the vertical, is being assumed by assuming, let's say, surface parallel flow. And what we know is that, of course, everything is not, let's say, in full equilibrium in the ice sheets. So there are quite some assumptions being made to make sure that we're missing critical observations there. So the vertical component that Harmony will be able to bring, because of course of our line of sight diversity, we have our 3 lines of sight. We'll be able to reconstruct based on, so both ascending and descending. We'll be able to get as well access to the vertical component. Then going to solid Earth, earthquakes and volcanoes, they shake the surface of the Earth. Understanding the processes involved there requires, of course, measurement of deformation and elevation change. Okay, this is probably the community that knows about this better than anyone else. It's important to define global seismic hazard and forecast volcanic activity. And of course, Harmony will be able, because of the fact that we'll be able to give this 3D deformation, will be a mission that will be able to give not only the north-south, but as well, let's say, the up-down displacement. So we'll be able to provide all the different motions in the different directions. So for solid Earth, currently, let's say, you know, we have only access mostly, let's say, to east-west motions, mostly sensitive to that. And it's clear that Sentinel-1 produced a really step change in our ability to measure strain. And this is for the Anatolian fold, let's say, with Sentinel-1. You see the Sentinel-1 InSAR GNSS does a fantastic job there for this mostly, let's say, east-west fold there. So Harmony, as I said, will be sensitive to all components, deformation including north-south. So then if you have a line of sight, let's say, provide, let's say, in this case, you have an east-west fold where you have GNSS only, then you have GNSS Sentinel-1, does a great job. But if you have GNSS Sentinel-1 only for primarily north-south fold, then of course you don't have sensitivity. And this is actually what Harmony will be able to bring. So Harmony will be able to reconstruct this and get sensitivity as well for this north-south fold. Coming back to the mission phases timeline, as I mentioned, say we have this configuration, the flying XTO and XTI phase, the stereo phase. Also during the stereo phase, we'll be able to reconfigure the system for up to 2 times per year to go back to this XTI phase. And this is really to make sure that we're able to as well have intermediate measurements for the glaciers and for the volcanoes during the mission lifetime. You see the overall mission products that we're able to bring, or products that are addressing the applications during the XTI phase, mostly ice volume change, glacier dynamics, volume change of volcanoes. And then we're as well looking at the ocean topography, which is experimental during this phase. Then during the stereo phase, when we are moving them apart, let's say, through 350 kilometer baseline, on both, let's say, between both the distance between Sentinel-1 and each of the harmonies. Then looking at 3D ice surface motion, air-sea interactions, atmosphere-ocean extremes, upper ocean dynamics, and tectonic strain. And then back in the 5th year, we'll be able to go back, let's say, to this XTI phase. And of course, this is different. Let's say this mission will be able to continue also afterwards. So the overall mission overview and observables. So as I mentioned, we have line of sight diversity for high resolution. We have slow differential InSAR and fast Doppler surface motion vectors in this configuration. So we have directional roughness, wind scatterometry, and improved directional surface wave spectra. Then, because of course we also have the thermal infrared instrument, we'll be able to see also sea surface temperature and cloud motion vectors over the ocean, and as well the cloud motion vectors by thermal infrared time lapse and height using the parallax between the view. So the observation concept for long track interferometry. I will briefly explain and say how this works. So basically, this is the green one, Sentinel-1. Sentinel-1 it's a pulse. It's being received, and as you see there, harmony will have 2 subapertures that will be receiving the pulse. Then if you give a bit of time, then of course the sea surface moves, and the next pulse is being transmitted and is being then received by the second aperture, which is then slightly, say there's of course 2 things that have changed. The surface has slightly moved, and the angle has also slightly moved, and this gives us of course then a small phase difference, which is then our interferometric phase, which we can then use to derive the velocities. What you see on the right is that we will have, let's say, the actual motion, the vectors that we see somehow, let's say, in the middle between the actual Sentinel-1 and Harmony satellites. So we get, in this case, we get basically 2 components of the velocity. Then for repeat pass interferometry in the stereo phase, we'll be able to see for standard repeat pass interferometry, there of course things are different. Of course we fly over once with Harmony, and then the second time, let's say, we see a change, which is also then translating in, again, let's say, an interferometric phase, which we then can observe slow movements in 3D with repeat pass interferometry. And in this case, of course, Sentinel-1 is able to provide as well a motion vector. In this case, you see basically the three vectors as you see on the right. Then, of course, we have the thermal infrared, as I mentioned, which is 4 basic channels: 1 panchromatic channel, and 3 spectral channels, basically covering, let's say, 5 views per satellite. And in this case, you see that on the right, you see that we have 3 overlapping views between the 2, which actually will be able to give access to height. So if you look at A3B1, A2B2, and A1B3, and then of course, then we have as well a distance between views with the same geometry. So A5 and B1, for example, that give you, let's say, then the time difference, which will be able to give access to cloud motion. And of course, you can combine all these 10 views in a way. And of course, during this time when the satellite passes over, between the first view of the tier and the last view, there can be something like 5 minutes time difference. And during this time, of course, the clouds are also evolving. The clouds are not just not only moving, but they're also, let's say, also growing, also changing. So this cloud dynamics features means that also we need access to as many views as possible, therefore as well the 10 views. So in the XTI phase, we have 3D surface deformation as in stereo, so we'll be able to continue this with 1 satellite, of course. And during surface elevation time series, we'll be able to do, let's say DEMs, single pass DEMs, and of course then we can do by flying over multiple times, we can do differential DEMs, and we can work, let's say, on surface elevation time series for glaciers, permafrost, icebergs, and volcanoes. The observation concept here is, of course, then we fly the two harmonies together. We have a perpendicular baseline, and we're able, let's say, by flying over, we'll be able to get access to the phase difference between the two received information. By getting rid, let's say, of the range dependency, we then get access to something like contours. We'll be able to bring up, let's say, the EM. As you see there, as an example from the Etna with the ERS-1, so quite some time ago. But of course, now what we can do is we can do it, let's say, instantaneous, let's say, with single pass, and we have a good revisit that we're actually able, let's say, to look at short-term, say, topographic changes with single pass across track interferometry. So what are our science primary goals? So I mentioned RC interactions, air ocean extremes, upper oceans. What do we need there? We need high resolution spectrometry, thermal infrared, and ATI supported for the RC interactions, as well for the air ocean extremes. But then for the upper oceans, of course, where we need to be the access to the surface motions, we use, let's say, the ATI, the Doppler retrieved velocity, and the thermal infrared as well. Then over land, glacier mass balance, cross-track interferometry, glacier dynamics. Of course, you can use both, XTI plus differential InSAR. And for tectonic strain, of course, is the stereo configuration, where we'll be able to do multi-directional repeat pass InSAR. Then coming to the actual development schedule and the key dates, where we are now currently, one ITT is out now for actual SAR development. So we start with the instrument first approach. The system ITT will become end of the year, early next year. Then we'll start to say the phase, what we call the phase B2. So now the phase AB1 is now the B1 is currently being concluded. And if you look at the development schedule, it may seem long for a lot of you, let's say, that we're until, let's say, 29 launch, but it's a very compressed schedule, and it's quite challenging to meet, but we do everything to do so because, of course, we want to make sure that the overlap with Sentinel-1D is as large as possible. We'll have a preliminary design review end of next year, early 25, and a critical design review in Q1 2027. So overall mission architecture overview. So I said 2 satellites flying together, being launched together on a Vega C dual launch configuration. Roughly the satellite is roughly, let's say, a ton each for each satellite. The tier payload is roughly, let's say, 50 kilos, so then you have an idea, it's about, let's say, size like this. Then the SAR is about 250 kilos for each of the SARs. What is interesting, I think, in terms of science data downlink, because, of course, of the we have 3 separate phase centers. We can the data science is about to say can go up to 1.5 terabit per orbit, which is quite high. And that's why there's also a reason why we moved to Ka band. We can work up to 2 ground stations, as Svalbard and Inuvik. Then overall looking at the ground segment, relatively standard ground segment, but of course things are different because we are using Sentinel-1 as our transmitter of opportunity, which means that we have to work as well with the raw data Sentinel-1 to understand and say, and to make sure we have the satellites synchronized with the data is fully synchronized with respect to Sentinel-1. So the Sentinel-1 data, let's say, will go, of course, standard to the standard Sentinel-1 PDGS, but then, of course, will come as well in the Harmony ground segment. Then there's one thing, because of if you've seen this type of tri-mode observation of the mission, there's going to be a multitude of products, and also a multitude of different product parameterizations, or some people may want to go for higher resolution, low resolution, or a different type of, when you want to combine differential, if you want to combine DEMs, you may want to look at different time scales. And this is something where we try to have a more, let's say, user interactive, let's say, environment for the user to develop, let's say, mostly, let's say, level 3 type of products. We call it multi-mission algorithm and analysis platform. The name will likely change, but the idea is that the user is going to be able to sit close to the actual data, to work with the data, and work with the algorithms in a kind of a cloud environment, which is open and public. Then my last slide is a summary. So Harmony is a data-driven, let's say, is it's a mission that's looking overall, let's say, at the order kilometer scale for the stereo and stereo phase. We're looking at sea surface temperature, cloud top motion, directional roughness, directional Doppler. It's C-band, so it's all weather, which is important for the extremes. Then we have, of course, 3D repeat pass InSAR for the global strain. And then as well, understand cycles of topographic change at volcanoes in the XTI phase, where we have a density DSM digital surface model time series, which is then in the order of 50 meters. So if you look at, say, things are going in the order from special scales from 50 meters to, let's say, kilometer, but in terms of time goes in the order, let's say, for 1 milliseconds to years in terms of the temporal scales. Okay, this was my presentation. Thank you. Okay, yes. I can do it, yes. Okay, then the next speaker is Paul Prats from DLR, who will continue where I left off in trying to exemplify and to show where we for harmony on the performance analysis and what was done in the phase AB1. So, yes, Paul, the floor is yours.
Thank you, Bjorn, for the introduction. So since Bjorn was doing already a very nice introduction to harmony, I can just go straight to the point. So the goal of what we've been doing together with ESA and the institutions you saw in the previous slide is to evaluate the performance of harmony for land applications, in particular for 3D deformation and for topographic change. And we have done this in 2 steps. First, by using well-known analytical performance models, extending them a bit. So you see here the example of a variogram for 3D deformation or just the standard deviation for topographic change. But also we have done more quantitative analysis by exploiting end-to-end simulations. In this case, by using forward models to simulate the data, then going through a simplified processing, and then comparing the results of this processing chain with the inputs that we provided. And this presentation will go through these 2 points, so analytical performance models, and also show the results of the end-to-end simulations. So I start with analytical performance models. For 3D deformation, we are basically taking, based on the literature, and extending it by using 3 lines of sight and adding additional error sources not included in the paper. And as well also as the mission phases, as we saw, we have this XTI 1 year, then 3 years stereo, and then 1 year XTI, and this needs to be also considered in the performance model. In addition, we also use input variograms for our performance models. In this case, just for the troposphere, please note that in this case, although I took the liberty, instead of showing the variance, I'm showing it in terms of standard deviation, just because the mission requirements are given in terms of also standard deviations, it's easier to compare. And so this x-axis, so the y-axis is, these are standard deviations. And we have, as we saw yesterday, very interesting presentations in the morning where we could see this evaluation of what happens when we use or we don't use atmospheric models. So here we are using both variograms with corrections and without corrections. I'm going to show now results for 4 scenarios, which are listed here. Scenario 1, it's an ideal scenario that we will not have in harmony. We would like to have 5 years stereo. So this could give us perfect, the best performance in the 3D deformation, but that's not what's going to happen actually. And then we have scenario 2, which is the ideal scenario in harmony, where we have the 3 lines of sight, both in ascending and descending acquisition. So this would give us the best performance in the north-south direction. We have scenario 3, where we have harmony only in one geometry, for example, Sentinel-1D with harmony ascending, and then Sentinel-1C in descending. In this case, of course, we will have less performance in the north-south. And then finally, we have scenario 4, where we could, in order to improve the performance for east, west, and vertical, we could exploit time series of Sentinel before the launch of harmony. This will be the 4th scenario. Here I put some simulation parameters, especially note the long track distance, about 350 kilometers. Temporal decorrelation, it's an exponential model, and we process to a resolution of roughly 100 meters by 100 meters. Here we have the results. This is the variogram for the 3D deformation, so for the three components. I don't know if you can read them. You see that there is one component which is constant. This is the north-south deformation. So the variogram, as you know, it gives you the standard deviation, in this case, standard deviation between any given 2 points as a function of their distance. And we see that the performance of the north-south seems to be independent of the distance between the 2 points. As I said, this is the ideal scenario. We will not have this in harmony. Then we have the optimum scenario for harmony, where we are close to this 1 millimeter per year. So we are just under the requirement of 1 millimeter per year for the north-south, while for east-west and vertical, we are a bit on top. I forgot to mention that the requirement is at 100 kilometers. So we have to take into account this line here. Scenario 3, where we only have harmony in one configuration, then gets worse the performance in the north-south. And in order to improve the performance for east-west and vertical, if we add then 5 years, in this case I think it was 10 years of Sentinel-1 before, or 5 years, sorry, 5 years in total, 10 years of Sentinel-1 then, we improve the performance for east-west and vertical. So observations, so as I was mentioning, for the north-south, we have a performance which is independent on the distance between the 2 points. And this is because when we make the simultaneous acquisition, because it's bistatic, it's simultaneous acquisition for all 3 lines of sight in one pass, the troposphere is highly correlated. And this means that when we are going for the north-south, it basically, mathematically, the inversion makes the cancellation of this tropospheric component. That's why we see almost an invariant dependence. So we also saw we can improve the performance of east-west and vertical if we add pre-harmony Sentinel-1 time series. And finally, so we achieve the goal requirement only in this 4th scenario, but the threshold requirement is achieved in all of them. And so these 2 millimeters per year. Now I jump very fast to the talk, and for topographic change, I don't need to say too much because actually this is very well known, and there are these InSAR performance equations. I put this paper for reference. And I show 2 plots of the topographic change accuracy. This is basically the difference of 2 digital elevation models. So on the plot on the left, what you see is the talk accuracy as a function of number of looks and height of ambiguity for a fixed SNR. And on the right, you have the talk accuracy, again, number of looks, but versus SNR for a fixed height of ambiguity. And what we can see is that, for example, if we take this particular case of for solid Earth with a goal requirement of 1 meter talk accuracy at 30 meter by 30 meter resolution, we see, and this is the cross you just saw coming up, we would need a height of ambiguity of 42 meters in this particular case for this SNR. But if, for example, you have volume, the correlation, or maybe the radar backscattering is lower, then we will have to push to lower heights of ambiguity, because we cannot increase the multi-look if we want to meet the requirement. So this means that we might have some challenging aspects, for example, if we use smaller heights of ambiguity during the phase unwrapping, and we need to think about maybe dual baseline phase unwrapping or other approaches. Of course, another possibility would be to average TNs before and after a given event, but this has to be done also with care, because maybe some processes are continuous. It's not just as a given event is happening. So far for the analytical performance. Now we go to the end-to-end simulations. So this, then you see this acronym, HIPS-Terra. This HIPS means Harmony End-to-End Performance Simulator. And actually, there were 3 developed during phase A. This is HIPS-Terra, and this presentation just shows HIPS-Terra. There was also HIPS-Mare for the ocean, and HIPS-Opti for the optical payload. HIPS-Terra actually consists of 2 softwares, independent softwares. The first one is the bistatic end-to-end simulator, which builds on previous developments under ESA contracts. And this actually generates raw data and includes also level 1 and level 2 processing. And this one was used for the XTI phase, to simulate products for the XTI phase. And then we were also extending, during phase A, we were extending the simulator we developed during phase 0, which in this case just simulates level 1A images, single complex images, and includes a simplified level 2, level 3 processing. In this case, we use this simulator to simulate both XTI phases, but also the stereo phases, the time series. So this slide just shows the coverage of the two simulators using this product tree of harmony. So you see the different columns, level 0, the raw data, level 1, level 2, and level 3. You have also the acronyms on the bottom. So the bistatic end-to-end covers all these products. As I said, we generate actually raw data and go until the production of the DEM, while the level 1A simulator concentrates starts on level 1 on co-register focused images. Due to lack of time, so I will concentrate only on the results we produced with the level 1A simulator. So first I give a fast overview of the simulator. Here you have the simplified block diagram, starting with the input data. So we are trying to use as many real data as possible, for example, reflectivity images from Sentinel-1, also true topographic changes measures, in this case with tandem mix. This is over Antarctic Peninsula, provided by NBEO. And also on the bottom, what you see is the deformation, north-south deformation. And actually, this was measured over the North Anatolian Fold, provided by Andy Hooper. And we were rotating it 90 degrees to simulate a fold in the north-south direction. So in the simulator, we generate actually the complex images, introducing speckle, reflectivity. We also introduce here the deformation. And of course, because it stops, we also consider the variation of the line of sight within the burst. This is what you see in the bottom plots for the ascending and descending configuration, no, for harmony A and B, sorry. And this north angle with respect, so the north angle of the two. And this is relevant, it's considered not only in the scene generator for the deformation, also in the error sources, as we will see next. So in this case, we simulate the troposphere for each epoch. Here, what you see is the difference between two given epochs. In this case, we were using the CWMF model to simulate these troposphere signals. Then for the ionosphere, again, you see the jumps because we are considering also the burst acquisition geometry of Sentinel. And in this case, we're using the Rhino spectrums to simulate these phase screens. And finally, we are also simulating clock errors, in this case, using tandem X realizations. So the radar module puts everything together, the complex scene, then introduces also the error sources, and in addition adds additional effects that we have in SAR acquisitions, like the azimuth ambiguities or also the noise of the system, thermal noise. Then here I just put some quick looks of some of the products we generate: coherence, interferometric phase, and wrap phase. And then finally, okay, just to note that for the particular case of the deformation, we have to simulate a large amount of images because we have we have both ascending and descending, and we have then for each we have 3 satellites, so we have to generate 6 stacks of images, 5 years. So this is about 900 images that we have to simulate, so quite a large amount of data. And then finally, we have these level 3 results, and then since we have the true that we were introducing as input to the simulator, we can compare basically what we retrieve with what we were introducing, and then make some statistics, as I said, variograms or histograms. Let's now go to see some results, starting with solid earth and volcanoes. So in this case, I'm focusing on this particular science case, Mount St. Helens, USA, as an example of volcanic dome growth. We were simulating here an acquisition with 40-meter height of ambiguity and a product resolution of 30 by 30 meter. You have on the left the Sentinel-1 reflectivity image. In the middle, you have the simulated topographic change. This was derived by LiDAR data provided by Judith Biggs from University of Bristol. And we can just zoom in and we see really quite large changes, more than 40 meters. On the right, you have the coherence. And then these are the outputs of this simplified processing that we apply. So phase, the unwrap phase, we are tricking a bit. We are not actually applying a true unwrapping, but since we know the true. So here we have the unwrap phase with noise, assuming we would have a perfect phase unwrapper. And then we have the estimated tog and the error. So we see some noise, some areas of noise here. This is due to lower backscattering or shadow areas in the dome. And then finally, we measure the histogram. In this particular case, we see that we don't meet this requirement of 1 meter. It's also, we are simulating this 40 meter, and the radar backscatter was not sufficient. As I said, one option would be to average DMs before and after, then our standard deviation improves accordingly. But of course, this has to be done with care. And so if we want to meet this requirement of 1 meter at this 30 meter by 30 meter resolution, we need maybe to develop a concept to try to use smaller heights of ambiguity or use dual baseline phase unwrapping approaches. Now I move to the 3D deformation. And in this case, we have again these 4 scenarios that I was showing before for the analytical performance. As I was mentioning, so we have this deformation in the North Anatolian Fault where we were rotating 90 degrees, and then we were exchanging the east-west deformation with the north-south deformation. So right now what we have is the actual east-west deformation that we have in North Anatolian Fault. Now it's in the north-south, which basically we have a fault oriented in north-south. And here now I'm showing the next slide, the results for this scenario I mentioned before, where we have harmony in both ascending and descending acquisitions, where we get the best performance in the north-south direction. This is, I'm jumping all the intermediate results, interferograms and coherences, and I'm just showing here the retrieved mean deformation velocity. You have vertical on the left, and the north-south in the middle, and the east-west on the right. And if we compare then with the true deformation, these are the maps that we get. Now the scale, so before we had about more than plus minus 20 millimeters per year, now we reduce the scale by a factor of 10. So here you see in the middle this effect I was mentioning, that the north-south performance, so it seems to be, we just see noise. There are some stripes there, so this tops this bus, probably due to the ionosphere in this case, or clock errors where we are sensitive to the jumps at bus edges. But it's mainly homogeneous, while we see clearly a trend in the other two. And this becomes more clear in the baryograms. So in the baryograms, you see the green dots represent the north-south deformation, and we see also in the simulation that it remains almost independent of the distance between any given 2 points, while we see the trends, so this increasing error for the east-west and the vertical. The plot on the bottom is the result of the analytical performance, and in this case, we see a good match between the two. Okay. Then we have, so I didn't show the results, just the baryograms for scenario 1. Remember, this was the ideal scenario. And scenario 3, where we have only harmony in one of the, on one of the geometries. And okay, this, we see a very good agreement in any case with analytical performance models. So, and this is just the last result to show. So in the simulations before, we were simulating an exponential decorrelation model with gamma long-term coherence of 0.2, which probably in some scenarios this is very optimistic, and maybe in some other scenarios this is too pessimistic. Of course, real data, it's different. So what we did, we were using the real covariance matrix, again, provided by Andy, and over the same area, using Sentinel-1 time series. So this is the 6-day coherence, and this is the 5-year coherence. And so in the end, I had this stack of coherences, which just for some given epoch, so I was interpolating to retrieve then the covariance matrix for all these 5 years. So, and you see in the 5-year coherence, some points, it's basically 0, the coherence. And here we have absolutely no long-term coherence. And of course, this is what we see. We see a degradation then in the performance. Especially in the north-south, we see a big jump, both in the analytical model, but also in the simulation, and this is also due to this large noise scaling for the north-south. Also, the east-west and the vertical degrade a bit, but not so much as in the case of the north-south. And then just the summary and the way forward. So we see first a good agreement between analytical performance models and the end-to-end simulations. We can say goal requirements are met, or threshold requirements in any case, but of course we have to take these results with care. I mean, there were assumptions done. We know that there are some scenarios that are challenging. For example, in the case we have no long-term coherence, or in the cases where we might have issues with phase unwrapping in overvegetated areas, where we have lots of volume. So, but that's the reason why we want to continue developing this end-to-end simulator to try to make it more accurate and more realistic. And this should be expanded then during the next phases of the Harmony mission. And the goal is not only to improve the performance prediction of the mission, it's also to support testing and developing of the level 1, level 2, and level 3 processing and calibration algorithm. This is also, I believe, one of the main outputs of this HIPS Terra simulator, especially working when we simulate raw data, and this allows also us to tune also the level 1 processor. So just if you want, I mean, this was very fast. I was just giving some highlights of these results of this study. If you want to know more details about that, you can link on here. This is the link of the user consultation meeting where you can find this report for mission selection that Bjorn was also mentioning. I think the slides are no longer available, no? And the videos are there. The videos are still there, so if you want to hear me again or Bjorn, you can go there again. So this concludes my presentation. Thank you.
Okay, thank you, Paulo. I think you can remain here because I think we have a couple 10 minutes for some discussions based on the and questions based on the 4 presentations that we've seen this morning. So just to recall, we had Explorer 7 biomass, we had Roselle, Sentinel-1 Next Generation, and then the Harmony mission, both, let's say, the overview and then performance analysis. So any questions, please go ahead. This is your chance.
Yeah, I have a question about the Roselle mission. Do you have an ionospheric mitigation strategy for InSAR application?
So we are currently looking into this, and what I mentioned during my presentation, there will be an ITT coming out in the end of the year, really focusing on ionospheric effects in urban data, and that will be part of the strategy.
Thank you for these nice presentations to give the overview of ESA. In the case of Sentinel-1 Next Generation and Roselle, you mentioned that they will be polarimetric capabilities. Could you give more details about how this will handle the type of data they will have and the details, if any? Thank you.
I didn't understand the last part of your question, but I understood to handle like how the quad-pol data would be handled or the different capabilities. So first, the focus for like Sentinel-1 Next Generation will be to serve, like to have like the same services as Sentinel-1. So that's like limited how we can play with the polarization, and also we always need to take into consideration that the orbit time is lower if we use different polarization. So it's something to discuss in the future. Maybe Malcolm can state on this, I'm not sure.
Yeah, sorry, I just arrived with the plane this morning, so I was hoping to sit in the background listening to people's questions. For Roselle, the baseline, at least as it's currently considered, is the dual pole mode. There is a fully polarimetric mode that's being characterized, and that is part of the capabilities of the system. But the one thing that we are looking at is the minutes per orbit, which are quite different for dual pole and for the quad pole. Keep in mind, dual pole is about 37 minutes per orbit, so a good chunk more time than for Sentinel-1 first generation, for instance. So we have another 12 minutes per satellite to play with, whereas for the quad pole, it's 20 minutes per orbit. So exactly how we are going to use that is still a little open to discussion, or open to consideration in the future high-level operation plans. Personally, I think it might be something like the strip map right now that you might know from Sentinel-1, first generation, which is used over selected targets from time to time, but that's only a first iteration at this point in time. To meet the needs of most of the services, they really want those 37 minutes, and you can imagine that we have to fulfill those.
Hi, I've got a couple of questions. The first is about Harmony. I guess it's going to be somewhat complicated to do all these retrievals for 3D deformation and topographic change. So will you be serving the level 3 products to make it easier for users or tools to make these derivations straightforward for us?
Yes, yeah. So mostly it's about, let's say, the level 3, mostly about retrieval models and retrieval algorithms. What we tend to do now is to make sure that everything is, let's say, we try to pursue open science, especially for the Earth Explorers. Given that these are science flagships, so I think the community should also be able to contribute and be able to use it. So right now we have already a number of ATBDs which are of course available. The tools are also going to be made available. And as I mentioned, especially for the level 3, there are so many choices you could have in terms of selecting, let's say, the final resolution of your level 3 product, the actual products to be taken into account. And as Paul mentioned as well, for the 3D deformation, you can select, let's say, you can take into account either, let's say, already Sentinel-1 from the archive, all these type of things. So there are too many things that the user really needs to take into account depending on his final application, the resolution of his final application, and the actual temple, let's say, the epoch that he is interested in. So these are things that are user parameterizable. This is the idea that we go in that direction. But of course, right now we are at the end of phase B1. As you've seen from the current, let's say, performance assessment that we are doing, we are quite mature already at this stage. And of course, this is not for nothing. It's because we have always been able, to say, to profit from what has been developed in the past in C-band SAR missions in Europe, and as well working on bistatic missions like SARCOM-CS. So we're not starting from scratch here. But this will be an ongoing continuation, and we will be able to share everything, let's say, with the community. And we hope as well that the community of Harmony will be growing, because of course we're now, let's say, it's quite a big science team, but of course we have time to have new ideas on the table, let's say, and people to actually use the data as it comes and try to prepare the mission with us. So I hope this answers your question.
Great. Yeah, I mean, I think maybe it's something that could be discussed in the specialist application sessions. You know, what parameterizations might be particularly useful for, if you're in a volcano observatory, having that really rapid access to topographic change, for example. But you've got the experts on the group as well to do that. So that's great. The second question was about Roselle and Sentinel-1 next generation. I guess it's linked to Harmony in that one possibility that was discussed maybe at the last Fringe was having a wide kind of burst overlap. So at the moment we can measure north-south motion in these burst overlaps, not particularly accurately, but we can get some measurements of north-south motion, and one could do that more accurately with a larger burst overlap. So has that been discussed at all for Roselle and Sentinel-1 next generation? Is it an option?
I think at the moment it's not part of the discussions.
Okay, maybe it'd be interesting to think
maybe
about.
It's good to bring it up. Like, I'm also taking notes for the summary session, and we can put it in.
Great, thanks.
Oh, okay.
No, it's okay, I come here. No, it's interesting because actually, Ricardo is here. Ricardo Lanari. Yeah, exactly. So we have to push now for it. You can talk if you want. Ricardo and his group, they were showing, I guess last year, right? You were presenting, so the option to do two look scans for Roselle. So, and without changing basically almost nothing in the system. And we could have 50% overlap. So it could be, this is what you were asking, right? Yeah.
Yeah, it's quite simple idea, Tim. It's because of the structure of the Roselle system, you have the possibility to exploit 5 single panels which are forming the azimuth direction of the antenna. And so if you properly change with respect to the actual design, the excitation of the 5 panels, you may increase your beam. And so you can easily get 5 looks. Of course, there is no free lunch, so there is some price to pay. So you lose some dBs. Let's say between 3 and 4 dB. So this is rather obvious because you are increasing your beam. So and also in terms of ambiguity, you lose a little bit. Now there are applications where losing a little bit in terms of noise equivalent sigma 0 and the azimuth ambiguities can be relevant. But of course, for what concerns differential SAR interferometry and the application you mentioned, we have seen this will be very, very relevant. There is a discussion. It's not an easy matter because clearly there are communities where even losing 1 dB, it's dramatic, while for us getting to azimuth looks will be fantastic. So we need to find a compromise about this. But the capability is there, and the solution is not very complicated, at least in our vision. I don't know if Malcolm wants to add something, but I don't want to ping-pong this microphone through the room.
No.
I have the feeling I should have taken the later flight, but okay. Now, as Ricardo has pointed out, there is the capability, that's for sure, I can confirm that. But please keep in mind that we're standing in front of one of the communities that uses Roselle, and there are many other ones, which also have very stringent requirements. And you might also remember that one of the successes of Sentinel-1, we call it now Sentinel-1 first generation, or FG, just to distinguish with the next generation, is the fact that we kept the number of modes to the strict minimum, so that what you get as a community, whatever community you work for, you get a guaranteed time series of well-calibrated and also performant images. And that aspect we would like to carry over to Roselle and to Sentinel-1 next generation as well. So the 3 to 4 dBs loss are perhaps small for this community, but they are huge for things like soil moisture, for sea ice, and so on, which make the equation very complicated. So we're looking into it, but that's just to explain the wider perspective on this, which goes beyond, shall we say, the pure needs of the InSAR community represented here.
Maybe just to mention, we at DLR, we have been also investigating this, and on Thursday we have a presentation precisely on these 2-look ScanSAR without modifying anything, just to look at the performance. We just need to convince then Nuno Miranda, I don't know if he's here, because if we do this, we will have to double the storage capability of the system. But we gain the 2-look for free. Anyway.
Any more questions? There's one down here.
Thank you, and thank you for the presentations. When you discussed the Sentinel-1 next generation mission, you explicitly mentioned the Vega C launcher as a requirement or constraint. Can you explain why? Where does the requirement come from?
So the requirement comes from because it's a European launcher available, and it's a mission from the European, like in agreement with the European Commission. So it's a requirement that's set. We cannot change it. Yeah.
Right.
But I mean, the launch is like 2032, right? So we hope to be better on launches at that time.
So it's not explicitly Vega. It just has to be a European launcher. Right?
It has to. It is explicit. So for Sentinel-1 next generation, it's explicitly Vega C. Yeah, it's for instance also when we announced the Earth Explorers, it's also very often limited to a specific launcher, and that's the same now for Sentinel-1 next generation. Because in the end, the satellite needs to fit the launcher.
Right, thanks.
Okay, last question, and then we have to close for a coffee break.
Okay, I have a question about the Harmony project. So I sincerely hope everything goes well, but I'm wondering if you have a backup plan if the unfortunate incident of Sentinel-1B happens again because Harmony is biostatic. If the main satellite is having an incident, then this whole project will be, just wondering if you have a backup plan.
Yes, thanks. Yeah, of course. One thing it could be, of course, a backup plan when things turn sour, which of course we hope are not going to be the case. But the other thing could be, of course, when there could be mission extension of Harmony, where there's no third generation any longer in orbit. So what is then the idea? And of course, we've been considering this, and we're looking at now, to make sure to try to see to what extent Harmony is also compatible with Sentinel-1 next generation. But take into account that, of course, next generation is currently just being designed. We're at the end of the phase B1. The B2 will only be kicked off, let's say, in the course of next year. But we're looking into, let's say, the two concepts currently under study, to what extent they would be able to be compatible with Harmony with its current design. So we're looking into this, and this, of course, and we'll try to have something that indeed will be able to continue, let's say, as best as possible. But of course, we have to take into account Sentinel-1 next generation. This is an operational mission. So we have to try to fill in, let's say, try to see what is feasible. And of course, everything depends on the final design. But surely, let's say, a certain degree of compatibility with Sentinel-1 NG will be there. Maybe not for all the applications, but there will be something. Yeah. Thank you. Okay, thank you all. So this concludes our session. Thanks for the audience. Thanks to all the speakers. We now have a coffee break until 11:10. So, yes, thank you.